All right, Math 201 students, this is the last pre-video for the semester over section 5.4 and 5.6. We're going to be looking at some applications of what we learned about integration. And this is called, section 5.4 is area and the fundamental theorem of calculus. So the definition of a definite integral, remember the ones that we've been doing so far, the antiderivative that we keep talking about in the integration, it was an indefinite integral. When we want to find a definite integral, we want to find the area bounded between a curve and two x values and usually the x-axis. So we're actually looking for an area of a region. So you're going to have what are called lower and upper limits on your integral. So notice a and b are on the integral symbol. So this says that the area of the bounded region R is equal to the integral from a to b of f of x dx. So this is called the definite integral with a as the lower limit of integration and b as the upper limit. So before we jump right in and tell you the fundamental theorem of calculus, we're going to look at an area that's easy to find by just using geometry. And then we want to show you that there's a rule to how we find these definite integrals and show you that we get the same answer. So let's look at this first one, and this is just a straightforward triangle. This is from 0 to 2 on the x-axis, so that's why this is 0 to 2. The function here is 2x, so we've graphed that line, and notice we're using the x-axis as a boundary as well. So when we go to find this area using geometry, so we're going to use geometry since this is a beautiful geometric shape. This has a base of 2 and a height of 4. We can just count our actual marks. So remember, in area of triangle, it's 1/2 base times height. So we would say that it is 1/2 times 2 times 4. 1/2 and 2 cancel out, so this is just an area of 4. Now, unfortunately, a lot of shapes won't be beautiful geometric shapes that we have area formulas for, so we need a better way to tackle this, and that's what the fundamental theorem of calculus is about. It says if f is a non-negative and continuous on a closed interval a to b, then our integration from a to b of f of x dx is equal to the antiderivative evaluated at b, which is the upper limit, minus the antiderivative evaluated at the lower limit. We don't have a plus c here because we're not going on indefinitely. And we're just looking at what is this difference in the two evaluations. So remember, big F is any function such that if you take f prime of that, you go back to the original function. Okay, so let's show you how this works for that same exact problem, but without using any geometry. So if I take this and say, okay, I'm doing from 0 to 2 of 2x dx. My first step is to take the antiderivative of this, which would be 2x squared divided by 2, so that's just going to be x squared. And instead of doing a plus c, when we do a definite integral, which means we have these numbers here, we say we're going to, and I usually use a bracket for this, we're going to evaluate this using the fundamental theorem of calculus from 0 to 2. Now, remember how this works. You do the upper limit first. So this is x, sorry, not x, 2 squared. So 2 squared, because that's the upper limit, minus the lower limit as the x, so that'd be 0 squared. So this is 4 minus 0, which is 4, which is the same area we just got up above. But we didn't have to draw any triangle out. We didn't have to know how to do the geometry. We just used the fundamental theorem of calculus. So let's do another one of these. This says evaluate the definite integral from 1 to 3 of x cubed dx. So with our newfound knowledge, we know that we would take from 1 to 3 of x to the third dx, use the antiderivative rules and get x to the fourth over 4. Bracket that in since we're not doing an indefinite integral. And we're going to evaluate it at the upper limit of 3 minus the lower limit of 1. So this would be 3 to the fourth over 4. That's the first evaluation, minus 1 to the fourth over 4. 3 to the fourth is 81 over 4, minus 1 over 4. This is going to be 80 over 4, which reduces to 20. So if we were to graph x cubed and actually look at the area between 1 and 3 and the x-axis and that curve, that has an exact area of 20. And that would be like units squared if we were going to put units on it. But we're just saying what is the area. Okay, so the only other thing I'm going to do in section 5.4 before moving on to 5.6 is I wanted to do one average value formula with you, and that way we just have one to do left in class, because everything else in between there is just using that fundamental theorem of calculus. So it says if f is a continuous function on a to b, which is bracketed, then the average value of f on a to b is this formula. So it's still a to b of f of x dx, but notice we have 1 divided by b minus a. So essentially what I like to think of this as if we had a function that does all kinds of crazy stuff, and we're starting, from one point to another, and we're trying to look for this area. Obviously this is going to be something that you couldn't do geometrically because it's not a nice geometric shape. So let's say that's my function and that's the area I'm looking for between an A and a B. What we're saying is that when we find the average value, it's going to be some height, and this is obviously not the right place, but it's going to be some height where if we were to box this in, the missing area here could fit in here and it would make a nice rectangle, okay? So that's kind of the idea behind this, is finding that height. So we're going to plug into our formula. So this is 1 over our a and b are 1 and 7. So 7 minus 1, the integral from 1 to 7, our f of x is 3x dx. So this is 1/6. And then I'm going to go ahead and do my integration part. So that would be 3x squared over 2 from 1 to 7. So this is 1/6, and then I'm going to work this out. So remember, you do your upper limit first. So this is 3 times 49, because that's squared, over 2, minus 3 times 1, which is 1 squared, over 2. So I have 1/6. 3 times 49 is 147. This is just 3 over 2. If we subtract, we get 144 over 2. So you could go ahead and do that. That's 144 over 12 by multiplying, which is 12. So that average value height is 12 for the function. Okay, and then that leads us just to one last section. I'm going to do a kind of an intro to section 5.6. We'll obviously spend more time in class on some of the details of these. But it says that this is the definite integral as a limit of a sum. Now, we're not going to actually make you do the limiting process very in detail. We're going to just teach you how to do it by rectangles in this course. There's much more to this if you were to take Calculus 1. So it says in section 5.4, we've learned that we can use the fundamental theorem of calculus to evaluate a definite integral if we can find the antiderivative of the integral. If we cannot find the antiderivative, we can approximate the area using the midpoint rule. So this is a way we could still find area if we didn't know how to take the antiderivative. Now, all of the ones we're doing, we kind of know how to take it, so there might be one at the end that I put in there that we didn't know how to take, but the idea here is that we can check ourselves on most of these. So this says use 4 rectangles to approximate the area of a region bounded by the graph of f of x equals x squared plus 1, and the x-axis, and x equals 0 and x equals 2. So they're just telling us how to draw our picture. And I do like to draw a picture on these because then you can see visually what I mean by the rectangles. So we have that, we're going to plot this graph. Okay, so, and actually I'm going to make the bottom bigger because we're only going from 0 to 2. So I am going to space that out a little bit more. So maybe here and here. Okay, so if we put in 0, because remember it starts at 0 for x, that would give me a positive 1. I usually plot the endpoints first. If I plug in 2, that's 2 squared, which is 4, plus 1 is 5. Do not assume that this is a straight line. It's a parabola. So I'm going to plug in 1 as well and get the point in the middle here. So 1 squared is 1, plus 1 is 2. So notice this is a portion of a parabola. And then we also have the boundaries x equals 0, x equals 2, and the x-axis, okay? So all of this together, this is the region that we're trying to find the area of, and I'm going to try and draw that in a little bit for you. So this is what we're searching for. Now, there's 2 ways you can do your rectangles in this type of problem, because the idea is that we are going to try to approximate the area by drawing rectangles in kind of and we'll use actual function values to help us draw those rectangles. But the problem is that we'll have some groups where you might overestimate your area, and there's another version where you might underestimate. So what you're going to hear me talk about is something called left endpoint rectangles and right endpoints. Now, another thing you need to know is that your rectangles have to have the same width. So since this goes from 0 to 2 and I want 4 rectangles, I need to make sure that I split 0 to 2 up into 4 evenly spaced regions. So since you can just think of this as a distance of 2, because that's what 2 minus 0 is, and we're dividing it into 4 groups. So 2/4 would be a half. So notice I'm going to mark 0, 1/2, 1, 3/2, because I'm counting by halves, and 2. Now, if we draw, and I'm going to try to make this a little bigger for this first part so you can see what I'm drawing. Let's make this 140. Okay, so let me scroll down. Just want you to be able to see what I mean by there's 2 different ways I can draw my rectangles using the markers down here and the function values. Now there are other ways, and the one we're going to do in class is called the midpoint. But if we want to use the left endpoints, that means the height of the function at each of the left markers. So that's the leftmost one is 0. This will be the next one, this will be the next one, and we stop here because we only need 4 rectangles. So if I was to draw these rectangles here, this would go over to this point and then come down. This would go to here, come down. This would go to here, come down. This would go with here and come down. Notice that this is going to be underestimating the area. Okay? And that's because we still have yellow above each of those. A different way we could have done our rectangles using, let's say, green, is I could have started with the rightmost endpoint for each of these, and I could have drawn that end. So we would have had, this goes to the end and down, so you go the opposite direction here. This goes to the end and down, to the end and down, and to the end and down. So we kind of meet up with each of our regions. So notice that this one overestimated the area. So neither one of them is going to give us a perfect answer because this has white spaces where the other one was missing yellow spaces. So what we're going to look at is how do you set up both cases. Now it's really easy if you know the function or if you know how to read it off the graph, because really all we're looking for is the area of each rectangle. So if we need area of rectangles, we need 2 things. Area of a rectangle is length times width. Now in this problem, your rectangles all have the same width if you think about that as your base. So the width here is a half, no matter which ones we're using, the gray ones or the green ones. So the idea here is that we just need to know what our endpoints are going to be. So if we're doing the left endpoints, we need the following 4 function values. And that's the first 4 numbers in our list. So we need f of 0, f of 1/2, f of 1, and f of 3/2. These are going to be length 1, length 2, length 3, and length 4 of our rectangles. They're going to be our heights, and that's all we need to find the area is a width times the length. So if we plug in 0, this is 0 squared plus 1, so that's going to be 1. If we plug in this is 1/2 squared plus 1, so that's 1/4 plus 1, and that would be 4 over 4, so that's going to be 5/4. If we plug in 1, that's 1 squared plus 1, so that's 2. And if we plug in 3/2, that squared plus 1, that's 9/4 plus 1, which ends up being 13 over 4. So if we're using left endpoints, then all we're going to be doing is saying each of my rectangles is the width times the height. So we have a 1/2 times a 1, plus the next rectangle would be a 1/2 times the 5/4, plus a 1/2 times the 2, plus a 1/2 times the 13 over 4. So this is going to be our area using left endpoint. So sometimes we'll call that area L. So we're going to work this out. So this would be, let's see, this is 1/2 plus 5/8 plus, I'm going to leave this as 2 over 2 because we're going to eventually get common denominator, and 13 over 8. So we need 8 for our common denominator, so that's going to be 4/8 plus 5/8 plus 8 over 8 plus 13 over 8. That's 9 plus 21, so that is 30. No. Is that right? 21 plus 9, yeah, 30 over 8. I'm going to double check myself real quick. So we have 9 plus 13 plus the 8. Yeah, 30 over 8. Okay, now usually that doesn't help you if you're talking about the approximation, so we'll divide it and get a decimal. So about 3.75. Okay, now if we use the right endpoints, I'm going to switch to blue this time just to distinguish. Everything is similar. Like, you're still going to use the 3 middle values we just found, like L2, L3, and L4, but you're going to leave off the 0 and you're going to use the 2. So you're overestimating since this function is going uphill. So our L1 this time is going to be f of 1/2. L2 is f of 1. L3, so these, remember, are just our lengths of our rectangles, is f of 3/2. And L4 is f of 2. So we already know these answers. This is 5/4, this is 2, this is 13 over 4, and this one we need to work out. So 2 squared is 4 plus 1 is 5. So then again, area using right endpoints is our width of our rectangles times each individual height. So this is going to be 1/2 times 5/4 plus 1/2 times 2 plus 1/2 times 13 over 4 plus 1/2 times 5. Okay, so we get 5/8 plus 2 over 2 plus 13/8 plus 5 over 2. Get a common denominator of 8 for each of them, which means we just need to adjust them again. So this will be times 4, so that's 20 over 8. So this time we have 25 plus 8 and plus 13, which comes out to 46 over 8. And I don't even care about reducing that because I'm going to immediately divide it to kind of get a decimal approximation. So about 5.75. So we know that our area, just by looking at the two different sides, the left endpoints and the right endpoints, is between 3.75 and 5.75. So those are, and those could be spread further out. Now, we could get more accurate if we made more and more rectangles in our subregions. So like, if we did 8 rectangles between 0 and 2, we'd be using like 1/4 for every single width of our rectangle, and that'd be a lot of rectangles to add up. So we're not going to make you do both right and left endpoints. You know, we'll either choose one, or we'll say use the midpoint rule, which is what we're going to go over in class. So this is just showing you that these are not perfect and they do over or underestimate the answer. Now I'm going to show you how to find the exact area of this region by using the integration. And that's the reason I'm doing that is because we actually know how to integrate that function. So we were going from 0 to 2 of x squared plus 1 dx. So we would take our antiderivative, which makes this x to the third over 3 plus x from 0 to 2, and that's going to be 8 over 3 plus 2 plus 0 over 3 plus 0, sorry, minus there in the middle. Talking too fast. Because remember, it's f of the top limit minus f of the bottom limit. So this is, let's get a common denominator, 8/3 plus 6/3. This is just 0, 0, so that's not going to do anything. So this is 14/3. That's the exact area. If you divide that, you'll see it's somewhere in between the ones we got. It's about 4.67. So notice we were overestimating a little bit on our left and right endpoints. Okay, so that is going to be all for the pre-video. We'll be doing the midpoint rule in class together. Hope you guys enjoyed this last pre-video for Math 201.